Today's speaker is Kateryna Hlyniana with the talk devoted to superposition of random mappings and Gaussian limits for thinnings of point processes. Please, Kateryna.
Okay, I will share my screen. Okay, and today I will talk about several types of transformation of point processes, and we will discuss their Gaussian and not Gaussian limits on their space. So I will start with such definitions and just don't understand what I will be talking about here. So we will start from a Poisson point process on line. So here today I will speak mostly about one-dimensional case for simplicity, but the result can be generalized for multi-dimensional case. So we consider random points in a space, and then based on them we will build such a field that will somehow weight their points or accordingly how much neighbors they have. So here if phi is some kernel that have for example finite support, then such integral will have a bigger value if point we have more points of a point process. And then we will discuss how we can iterate such fields and what kind of statistics we can consider, and we will discuss such average over a long interval or big window in a multi-dimensional space, and we will see what kind of limits we can expect here. So main limit, of course, will have a Gaussian distribution and normalization as usual as in the central limit theorem we will have as square root of n, but we will consider some cases when we will have another kind of limits and another normalizations. So once more, so we start from point processes on their space, and then we will consider like here basically two models. One is some sort of linear model on the configurations, and another is non-linear, and we will see what kind of limit theorems we can get. And another generalization we will get also to this transformation Gaussian noise to environment, and we will see that the correlation of this Gaussian noise will change normalization and type of limits. So let us start more precisely. I remind the main local fields that we built on random point configuration, and well, if phi is non-negative, then you can imagine that, like as they say, that we create a field that become bigger for more crowded places and less for not crowded places. So then we can consider what kind of iterations we can have, because my first idea was to consider dynamical system on random transformation of configurations of points. So we will here I will consider iteration as time. So I iterate with this time point process and what we can get in the bigger time. So here time is discrete. So one of the possible construction of dynamics on point processes is to define such random fields iteratively. So we start from one field as before, then we can define such weighted measure that will concentrate on initial Poissonian points, but now it will have weights. So you can imagine that we assign to each point its like number of neighbors. And then based on this new point measure, now it has weights, we will create next field that again with somehow it will take even more into the account neighbors, and we can consider such iterative random field and iterative point processes. So I will call this model linear because we have a linear transformation of a point process. I will show it the next slide. But before go to this justification why it's linear, I will introduce the statistics that we consider. So n small here is corresponds to time. So we consider like discrete time, and n capital we will be integrating over a larger and larger window of the such new measure. And in general, idea was to try to prove the limit theorem when interval tends to infinity. So interval grows and time as well. But for now, it's just not done to the end, but we have some ideas what to do with this. So why I call this transformation linear? Because I recall we have such a recursive transformation of fields, and if I denote that by t mu, so mu the space of the initial Poisson point process I fix, and now we run in transformation with time. So if we write such integral operator, then next iteration of field f is just integral operator, and it's linear. So some sort of, that's why I call this transformation linear. And this will be opposite to the next type, because when I thought what kind of iteration we can get and what type of evolution of point processes more interesting, I try several models, and we got some results for both of them. So another type of how we can create such iteration is now to consider Okay, so we start from the same field with weights of point process, but now we use here transformation, which here we take just a convolution with weighted measure and the kernel itself. Now such transformation is a little bit more different and more difficult because now it's non-linear. So mass that we create from initial point process will create such non-linearity because of convolution of phi. So if using notation of convolution, so now what is the operator for iteration of point process? Now we are making a convolution. So here, if I start from initial Poisson point the process, next one will be convolution with fields that I built on their initial point process. So I will give some examples like when this coincide and when not. So we start here just for reminding what objects we consider. So we start from such iteration of fields or iterations of such form linear and non-linear. So for the first iteration, we have the same. So we have the same first field based on initial point process, and we create the next measure that the same. We just multiply by weight of obtained field. But on the step 2, we have now the same fields. We have the same fields because we build them as integral with respect to here we integrate with respect to initial point process times previous field. Here we integrate by convolutional point process. But now fields will be the same, but point measures that we consider, they are different. So for example, in nonlinear case, we somehow multiply history. So we take field at time 1 and we multiply it with field at time 2. So somehow we track here history of weights. But in linear case, we just take the last field and multiply it by Poisson point process. So they're the same for just for first iteration, but their second and so on steps will be different. So, well, actually, I discussed this, the main difference in non-linear case that we consider here history of how waves accumulated. And as for statistics, because we will consider limits of statistics, and here for linear and non-linear cases, I show just the difference for n is equal to. So for n is equal to 1, they coincide, and already on the time of iteration 2, we will have in linear case, we can just integrate with respect to measure times previous field like existed field, and for nonlinear we track history. here I just added a picture of simulation to understand how field is built on a Poisson point process. So we know that a Poisson point process like is a one of example of some sort of when we choose points in space uniformly, but the investigation of such fields built on point processes with a kernel can somehow amplify regions with crowded more crowded regions and suppress regions without points. So here we can see how fast this amplification of crowded places occurs. And so here you just imagine that this yellow dots is our new measure, so it will be a weighted measure which we will investigate in this talk. So their main object now is to consider what kind of limit and what kind of normalization we will use here and what interesting we will have. So here I just want to stress once more that such dynamics, my idea was to investigate the dynamics that depends on neighbors of points. So this some sort of the dynamics of points with interactions. So if, for example, a point have a lot of neighbors, it can evolve in one way, if less, then in another. So this initial motivation was to consider dynamic of points that take into account the location of neighbors. And here this dependence on neighbors is defined by a kernel phi, which can be smooth with infinite or finite support. So let us consider the first statistics. So this will be just integral over larger and larger interval minus n, and we will integrate a bounded one periodic function f. So here the periodicity of function f small is chosen because for simplicity to apply of central limit theorem. So the idea that we will have is to split a big interval to to sum of unit intervals and to see if we can apply to this sum of integrals over unit intervals central limit theorem. So here, if I write this statistics in term of I substitute just kernel phi and I write summation over points u and v from initial Poisson point process. So here we can see that already first statistic involve the dependence between 2 points in point process mu. And so one simple example for understanding, like if I take for kernel just indicator of interval from minus RR, then first field F1 will just count the number of points of the interval with center B and length 2r. And then the first statistic, well, we write like this. So we take summation over all points from Poisson point process, and we sum the number of their neighbors. So we somehow just write summation over for each point we sum their neighbors. So their case which is more simple and I will start from is that when the kernel phi, which I consider for construct the first field over point process has finite support. This simplifies a lot the proof of statements, but it can be generalized to phi with this good for the case when phi of x tends to 0 quite fast when x tends to infinity. So as I told, the idea was to divide big interval minus n to unit intervals, and now, well, we need to use that phi has finite support, and we know that values of Poisson point process on non-interrupting intervals are independent. So if we take two intervals quite far, one from another, then the values will be independent. So from this, we will have that summands in this integral statistic are m-dependent, and we will have standard central limit theorem. Why I am saying standard? Because we normalize this n, which is proportional to variance of statistics, and it will converge to Gaussian random variable with some variance or sigma 1. So as I said, the idea of proof is to represent statistic as sum over as sum of integrals over unit intervals, and because we have finite support of phi, we get that xk actually m-dependent, and here we can apply m-dependent central limit theorem. So I'm sorry, this is okay. Now for bigger n. So here I didn't write linear or non-linear because for first iteration they coincide. Now for what we will have when we apply n iteration for our model. So here the case is still quite simple because, well, because of finite support of a kernel, even after n steps, we will have m dependency of summands, as I told, but this m will grow with number of iteration. So let us see here. Again, we divide integral over large domain minus nn into integrals over unit intervals, and from representation of linear iteration, we will have that with such value of m, here it depends on n, we will have m dependence of this x. So again, we can apply central limit theorem for m-dependent random variables. And about limiting variance, here still quite complicated to calculate it because we need to compare their covariances of this integrals over interval 0, 1 and on a far distance over k plus 1. And it's quite difficult to track it over number of iteration, but this is one of the questions that we're working on now. So here the quite interesting but complicated question is to either get the recurrence formula for variance with respect to n, or just consider its growth with respect to n, or with respect to initial, with respect to intensity of initial point process mu. For nonlinear dynamic, we have almost the same case because, like, again, this simplifies a lot the application of central limit theorem. So for this case, again, we will have the same number of m dependence of nonlinear k for x their integrals over unit intervals, and well, the variance will have the same form. So this is their main results for this dynamics. And first of all, like we were expecting that maybe we will get something non-Gaussian because of convolution of point measure, because the field that is generates. So because here nu n is not integral with respect to just initial point process mu. Here we take a lot of times a convolution in this field that it's generates, and again we take a convolution. So we somehow expected that because of interaction between points, we will have some sort of maybe non-Gaussian limit, but here everything is Gaussian. So to get some something more interesting and not Gaussian in limit, we decided to add randomness into random transformation of point processes. So as before, we will start from Poisson point process, and we will construct this first field based on points. But now for we will consider statistics that use random, well, Gaussian weights over their field over a point of Poisson point process. So somehow we will add dependency, because I consider Xi to be a Gaussian process with some arbitrary covariance function. So in this case, you can imagine that we not only add weight to points that depends on number of neighbors, but also we add some Gaussian noise such that the distant points somehow dependent because of this Gaussian field. So here I will just consider first iteration. That's why I don't generalize it for dynamics with respect to time and small. So this case is quite interesting, and from one hand side simple, from another hand side it gives quite interesting results. So if we fix our measure mu, so I fix Poisson point process, then this statistics, so mu is just some point measure non-random, and phi is built on this measures as a convolution. So they defined by point process itself, and with condition on this, we will have just Gaussian random variable. So this random this Gaussian variable have variance which I denote by V sub n capital. So this is variance if mu is fixed to point measure. Then using just variance of integrals of Gaussian random variables, we get this formula for variance. So I'm sorry. So this we get from here V from W from V is just integrand f that we use for statistics time as field based on point process. So here now rho is a covariance function of Gaussian field, and now, well, we have this statistic is conditionally Gaussian. So if we want to have a limit of this random variable when n capital tends to infinity, we should know how variance grows. And based on growth of variance, we will know how to normalize and what limit to expect. So to analyze the growth of variance, it it depends on how this integral over covariance function behaves on infinity, and if it's integrable or not. So if we consider this like double integral of covariance function of Gaussian field, then we can have several several cases how it can grow. So if we have the case when Gaussian random variable have covariance from L1, then expected growth will be like n. If rho is has such asymptotic on infinity, then growth of this of variance will be of such form. And when it is not going to zero infinity, then this value grows like n squared. So here we have a different regime based on their how we choose Gaussian field for our statistics. So the idea of proof is now is the following. So as we told, the statistics that we considering under condition of Poisson point processes normally distributed with variance Vn, and if I consider now deterministic normalization, so now I am asking what normalization I should use to get limit. So if I consider characteristic function of this statistic, here I divided by normalization that depends on n. So we have this formula. So it's quite simple idea that now we need to find the normalization A that such that B that the variance of this Gaussian variable normalized by square of A will have some limit. And from this, we can get the limit now. So here we actually don't use central limit theorem for m-dependent random variables. As in previous cases, here everything is like we have another idea. So here we can use any kernel to build a field over point process. Here the leading role plays the Gaussian fields that we like noise that we add to our measure. So from this formula, we can have two cases. So in one case, if under some normalization, variance will converge to non-random value, then their limit of statistic will be Gaussian. Now, if limit is random, here we will have a more interesting case because now limit will be non-Gaussian. So if normalized variance converge to random variable in distribution, then the weak limit of normalized statistic will be this, will play a role of random variance of limiting Gaussian distribution. So their idea is enough, like their idea now is to understand how this variance grows, because now here we have integral with respect to Poisson point process and with of Gaussian covariance function. So like I started before from analyzing how this integral grows, and actually we will see that this is natural choice of normalization for this conditional variance. So for the simplest case, when Gaussian field has integrable covariance function, then as I said, we will have their such asymptotic. And as for another more general cases, I prove the statement that variance should be normalized exactly by this integral Rn. But here we need to have some conditions on infinity for covariance function that says that it does not jump too fast, so the derivative is on infinity is not big, like it goes to 0. So under these conditions, we can use this kind of normalization for statistic. So, and we will have this okay, it's now not central limit theorem, now it is just limit theorem, because in normalization we use, well, different asymptotics. So here this asymptotic will be different. So here I assume this value. So I recall that here we can have such different types of normalization of such kind. It depends on behavior of covariance function. Oh, here recall once more. So here we see that compared to statistic where we didn't use Gaussian noise, we need to use different normalization. Now, as for this, for now we discussed when their variance, normalized variance of statistic converge to constant. Now, how to get a random limit? For this case, we need to have some additionally to we should have one common Gaussian component which we will add to all points together. So in that is, if we consider a covariance of such form, then we can prove that the normalized variance will converge to random variable. So here I just consider one simple example just to show the way of calculation. So the idea is so simple here. So if Gaussian variable just do not depend on u, I'm sorry, a Gaussian field is the constant, that does not depend on u, then we can take away this Gaussian random variable, and now this integral will have under some normalization will have their random limit, and so we will have here a product. So how to see that we have here random limit? So we take their variance. Okay, this the random variant, the conditional variance of this statistic, and now we need to know how it grows. So now this is quite simple statistic that we built on usual point process, and to this one we can apply central limit theorem like we started from. I'm sorry. So we started from just okay, we can consider just usual integral with Poisson point process, and for this using the usual statistic we will have Gaussian limit. So under such in such case the variance normalized variance will have limit of square of Gaussian random variable. So here the interesting result is that we have non-Gaussian limit for this case, even though normalization is standard like square root of n. But in the limit we have this mixture of Gaussian random variable and variance like we take from this limit. Okay, so now, as I told, the main idea was the following. I want to construct the iteration of transformation of point processes and consider then consider limit theorems with respect to space and with respect to time. So we somehow want to see what will happen after infinite iterations. So, but their proof that we use that I started where we use m-dependent random variables is like quite challenging to track, because this step is like that doesn't work due to, okay, if we take more iteration, more we have m dependency, and it's quite difficult to track the dependence, how we should compare number of iteration and growth of window. So because of this difficulties, we decided to consider a slightly more simple model, which doesn't have this problem, but it has some sort of iteration of transformation. So now I consider another model that will be constructed from convolution of point measure with I'm sorry, it will be a point measure we will fix here, and we will consider convolution of kernels. So somehow you can imagine that we start from each point of Poisson point process random walk with distribution phi, like if you can imagine phi is density of a random variable. Then convolution will give you their j steps of random walk, and then we will consider field built on this convolution, and here we weighted with respect to initial point process. So somehow we well, we diffuse all points and then we count their neighbors of diffused points, how many we have them. So somehow this field is much more simpler with the previous one, because here we just make the convolution of kernel j times, and then we consider this field that we built on initial point process. And then we consider this linear statistic with respect to such field. And now the same question, what kind of limit theorem we can expect for it. So here once more we take the convolution of one field phi, so we don't change weights of initial point process. So we just first make the convolution smooth, and then like here, and then we integrate with this initial original point process. Even though this case is simple, but it like it makes us to consider infinite iteration of such dynamics. So as for comparison between linear model and this convolutional model, so you can see that for the first statistics, actually they coincide. So this was our different ideas how to iterate statistics, like how to iterate transformations. So one of possible transformation is to make a convolution of field itself. So here we got the result, which is formulated as following. So we can take time Jn, which is growth at not faster than O small of n. So, and with one another condition that if I take the Fourier coefficient of function f that we integrate, then like I should have this condition where this is Fourier transform of kernel phi, of kernel phi, so it should grow to infinity. So this condition should satisfy also. So then under such condition, we will have central limit theorem. So here I write that we should use normalization of variance of statistics, and for now, like I considered some examples, and here in most cases we will have square root of n normalization. And their idea of the proof, based on that this statistics actually, so I want to show it. So we integrated here with respect to Lebesgue measure this field, which was built on Poisson point measured convolution of kernels, and changing order of integrals. Actually, we can write it as integral over a function psi, here I write, of Poisson point process. So here, this case just the case when you need to investigate the growth of integral with respect to Poisson point process. And one of these results was obtained. So here I write a condition like what we should do. Like we normalize with respect to variance, and we will apply next central limit theorem for Poisson integrals, and the condition there, this result I show that the Wasserstein distance between integral over Poisson point process and Gaussian random variable is bounded by cube of integrand here. Here alpha is intensity measure of point process. So here to get convergence to zero, I'm sorry, yes, to zero, we should have this condition, and we check this, it holds exactly under this condition that I write here. So also I want to okay, yes, so here just I wanted to say that the growth of number of iteration here, well, it can be as finite as infinite, like for example, like square root of n or a little bit more. And in any case, we will have a Gaussian random variable in the limit, but here we didn't finish this calculation yet, that like to find different asymptotics of variance and different growth of number of iterations. So this is still we are doing. So, and I think that's all, and thank you for your attention.
Okay. Maybe someone have questions or comments, please. Katya, still I think that it will be very interesting to get the limit description of the limit not only as one Gaussian variable related to function f, we standardize it, but as some colored noise, where we will specify the variance of the limit, its dependence on f.
Yes, this is also what we want to like. I wanted to present something, but I didn't manage to write some nice formulas. Yes, so for even for this limits, for example, for different number of iterations for different functions. Yes, like this somehow to consider correlation of this to Gaussian, or just to find this Gaussian field together. Oh, it's interesting. But for now,
Yes, because
I didn't get some
it looks like
analyzed
we can
results.
think about the description of the evolution in the time n to this Gaussian like mean field approximation, yeah, for this point process. And the trouble is the same as we did in the process of points which survive in the Aratia flow up to the moment t.
Right.
Okay. hope it can be done. Yeah. Okay. Maybe someone else have some comments.
And I want to ask, and what happens if we tend to infinity both time and small and this space parameter and capital? Both tend at some rate.
Yes, so
Is it
so
Mhm.
yes, so here that okay, yeah. So here what I say that well, the rate of convergence here, like in the last case with what we managed to consider, that under this condition we know that variance tends to infinity, but the exact formula, how it depends on n and the number of iterations here, jn is number of iteration, I don't know. So they can grow together, but maybe we can have slightly different rate of growth of the variance compared to square root of n, like of n. So in this case, like we got the limit statement for those models that I started to when we add weights to points of Poisson point process. There still we didn't finish the proof of like if we can get their central limit theorem.
Okay. Some other questions, please. If not, then thank you for interesting talk. And as far as I understood, next time will be our joint talk, me and Kateryna Koshtareva, about some Gaussian random curves.
Yes.
So for today, that's all. Thank you for attention and see you next week. Bye.
Thank you so much. Bye.
Goodbye.